This video, I'm just going to read through the notes just in case you can't understand my penmanship. Chapter 5, Extra Notes. Series resistors add up to get the total resistance. If you can hold the pencil down through the complete path, the resistors are in series. Series resistors have the same current through them. Series resistors have different voltage that is dropped across them, assuming the resistor values are different. Kirchhoff's voltage law. Right? Kirchhoff's voltage law says that the sum of voltage drops through a series circuit equals the total voltage. So basically when you go around the closed loop in that circuit, the voltage drops across the resistors will all add up to the source. And likewise, the series circuit, since there is only one path for current, the current value is the same. If using Ohm's law to find voltage drops, you will use the same current number multiplied by each resistor value individually. Okay, as an example, find all voltage drops. So we have a 10 volt source, a 2K resistor, a 3.3K resistor, and a 560 ohm resistor. So we're going to use Ohm's law first. So I can see that these resistors are all in series as there is only one path for current flow. So if I just trace back that path for current flow right here, starting at the source, just going around this loop, I see that there's only one path for current source all the way around. Okay. So therefore, the total resistance is equal to the sum of the three resistors. So I just put the three resistors in and I add them. Now notice when I add them, I don't just add 2 plus 3.3 plus 560. I need to take the K and convert it to thousands. So it's going to be 2,000 plus 3,300 plus 560. Or you get a total of 5860. Or moving the decimal place over 3, you get 5.86 kiloohms. The total current is total voltage divided by total resistance. Notice all my subscripts are T's for total. So when I take my total current, I need to divide by total voltage and total resistance to get total current. I can't divide by, one voltage drop to get well, never mind that. Okay, so total current is equal to the total voltage divided by the total resistance. So I take the total current. So I get my total voltage is 10 volts, and I divide that by the total resistance, which was that 5860 number, and I get 0.0017, or then moving the decimal place over, I get 1.706 milliamps. To find VR1, VR2, VR3, now that I found the current through the resistors, 1.706 milli, all I need to do is take that current and multiply it by the resistor, and that'll give me the voltage drop. Current through R1 multiplied by the resistor value R1 will give me VR1. So 1.706 milli times 2K. Again, I take the metric prefix and I have to convert it. Milli is times 10 to the minus 3. K is times 10 to the third. So that gives me 3.4 volts across resistor 1. VR2 is the 1.7 times the 3300, which is 5.63. And then finally VR3 is the 1.7 milli times 560, it gives me 0.99. Now notice when I add up these voltage drops, V1, V2, V3, I do get 10 volts. Well, it's close enough. If I didn't round, it would have been right on. Okay, now using voltage divider formula. So basically you can use Ohm's law all the time, but this is voltage divider formula is just another way to get voltage drops. It basically takes the proportion of one resistor with respect to the total resistance multiplied by the voltage source. It gives just the proportion of voltage that's dropped. So you're really not even using current to find this one. So the formula V1 would be resistor 1 over resistor total times source, resistor 2 over resistor total times source for V2, and V3 is resistor 3 over total times source. So notice the R1 over RT, the R2 over RT, the R3 over RT, those are all the proportion of R1 with respect to RT. It gives you the ratio. Okay, so anyway, I just plug in my numbers. R1 was 2K over 5.86 times 10. Again, I got that 3.4. It's the same number I got with Ohm's law. 3.3K over 5.86K times 10 was the 5.63 volts. And V3, I get the 0.955. Again, I got the same exact values. And notice no current value is needed for voltage dividers. Power dissipated by each resistor needs its own formula. Power 1 would be V1 over R1, or again, I'm using my basic power formulas, V squared over R, V times I, or I squared R. The only difference here is I'm using all the quantities that pertain to that particular resistor. If I'm looking for the power dissipated by resistor 1, I have to use the voltage across resistor 1 with resistor 1. I have to use, for the second formula, I have to use the voltage across resistor 1 with the current through resistor 1, or for the third formula, the current through resistor 1 squared times the resistor 1. So again, here it says, notice I'm using all ones, meaning ones as my subscripts. To find the power dissipated by R1, I need all the resistor 1 numbers, meaning V1, I1, R1, all that. Here's all my formulas for power 2 and then power 3. So V2 squared over R2, V2 I2, I2 squared R2, P3 is V3 squared over R3, P3 is V3 times I3, and P3 is I3 squared times R3. Because this is a series circuit, my current values are all the same, meaning when I found my I1, my I2, my I3, they were all what my IT was, because there's only one current path. So if I use my power 1, if I use my voltage formulas, I can go V squared over R. So I just take my V1, that was my 3.4, divided by R1. I get 5.8 milliwatts. Power 2 is the voltage drop across resistor 2, which I calculated to be 5.63 squared, divided by 3300, which is my 9.6 milliwatts. And power 3 is 0.955 squared, divided by 560, which is 1.63 milliwatts. Total power is all the powers added up, P1 plus P2 plus P3. So if I just take all those three numbers I just calculated, 5.8 milli, 9.6 milli, 1.63 milli, I get 17.03 milli. Or I could use a total power formula. Again, it's the same power formula, I'm just using all my total quantities. So I can say total power is voltage total squared over RT. So you must use total voltage and total resistance to get total power. My total voltage is 10, so I go 10 squared, and my total resistance was 5860, so I divide that 10 squared, or 100, by 5860, and I get excuse me, 17.06 milliwatts, which is exactly what I got when I added my 3 powers up. That's close enough. The small difference in numbers is due to rounding too much. And then I just showed you over here using the other power formulas, I squared R or V times I. Again, I'm using total everything. My total current squared times R. T gives me the 1706 again, milliwatts. And then I use voltage total, I total. Again, I get my 17.06. So it says all the same numbers. They're all the same numbers, so I can use any of these formulas. Any of these formulas will work.